Greetings, everyone. Welcome to the 18th International Conference on Artificial Intelligence and Law, hosted by University of São Paulo. My name is Rafael Saravalli, and I'm going to open the floor of the first panel of the fourth day of the event. But before that, in the name of the ICAIL organization, I'd like to thank our platinum sponsors, Jus Brazil and Albert Einstein Israeli Hospital, our gold sponsors Logarithm, Legal Code, and PG Lawyers, and our silver sponsors Urbano Vitalino Lawyers, Opsi Bloom Lawyers, and Oasis Open. Now, I'd like to introduce you Mr. Lukasz Korski, who will present and answer the paper with the title Explaining Artificial Intelligence, Lawyer's Perspective. Mr. Lukasz Korski, you have 20 minutes for speech. Afterwards, we'll move on to the questions. The stage is yours.
Thank you. Just let me share the slides. I hope that the presentation is visible now. And let me begin. Explainability has always been at the heart of artificial intelligence and law curriculum. The growing popularity of deep learning methods makes inquiry into deep learning explainability even more important. Moreover, it is of value not only in artificial intelligence and law, but also in general artificial intelligence research. In this work, we aim to quantify and test the usefulness of different explainability methods when applied to the area of legal text classification. Those methods were evaluated using the opinions coming from the legal professionals. This work was performed by Sashika Ramakrishna from Free University Berlin, as well as by me, and I am currently employed at the Interdisciplinary Center for Mathematical and Computational Modeling at the University of Warsaw. This talk will be structured as follows. Firstly, I will start the presentation by stating the research question, and I will also refer to our previous work to fully present the motivation before the research undertaken here. Secondly, I will talk about the computer system we have designed and implemented for our experimental explanation generation. The discussion of systems architecture will be supplemented by the review of dataset that was used. Finally, I will describe the results of the pilot study that we conducted based on the explanations generated by our system. So to begin, when the motivation is concerned, it should be noted that this work is a significant extension of our previous paper presented at the ICAIL workshop during the previous Zurich conference, with extended version accepted into ICAIL proceedings. In this aforementioned paper, we have presented a classification system that was based on convolutional neural network, and that system used GradCam method to highlight the most important words when doing the legal text classification. However, the choice of GradCam as an explanation method was somewhat arbitrary, and in the work presented here, we explored different methods of explanation generation for convolutional neural networks. Thus, with the work presented here, we aim to give a more structured and rigorous means of assessing different existing explainability methods. In general, there are three main categories of methods that can be employed for convolutional neural network-based explanation generation. Firstly, already mentioned GradCam is commonly used in computer vision. It uses the gradients of the target concept that flow into the final convolutional layer, and it produces a coarse localization maps that highlight the most important regions in input data that were the most important for predicting the concept. The second method that is presented here is SHAP. It is a game theoretic approach that aims to explain the output of any machine learning model, and it generates explanations using the Shapley values from game theory and their related extension. And thirdly, LIME is an example of surrogate model-based diagnostic, and it builds a local interpretable model based on the perturbation of input data fed to the model. Thus, to sum up, in our research, we wanted to uncover what lawyers think of explainable artificial intelligence systems and of the methods that can be used in those systems. The tech cloud presented on this slide comes from the survey we have circulated among legal professionals, where we asked them about their views on what features they would desire from explainable artificial intelligence-based system. Generally, they talked mainly about tools that will take the burden of manual work away from the lawyer. Many people mentioned a transparent decision process, but as will be shown later in my talk, the conceptualization of transparency varied in the opinions given by various respondents. Another thing that may be noted is that when we ask about explainable artificial intelligence, many respondents were talking about general artificial intelligence system. Thus, they were viewing those two terms as, in a way, synonymous. And in conclusion, we may say that explainability for a lawyer is a crucial feature of the system, and it is indispensable in their mind, and it is a necessary element of any artificial intelligence-based system for law that can be used by the lawyers. Moving on to the methodology, we have built a modular system. In its heart, it has a convolutional neural network, like here. The implementation of the networks that we have used was sourced from an external authors and used with their permission. We have used the system developed by Hebin Shin, which was based on theoretical insights from Yoon Kim. Our core contributions to the system is the extension of the embedding module to support various embeddings, like what2vec or BERT. Secondly, we have introduced artificial intelligence and law-based datasets to the system. And thirdly, we have added pre-processing tools as well as a metric comparison module. This metric comparison module is based on the insights from computer vision and uses a well-known set of metrics to generate insights into how the system works. In the experiments that we present here, the convolutional network was trained on the PTSD dataset. For testing purposes, we allow a user to choose a variety of embeddings. However, in this research, we have settled down on using distribut-based embeddings. Though other versions of the systems I have already said allow to choose another set of embeddings. The part that will be crucial in this presentation is the fact that the CNN module was coupled with the visualization module, which generates Heatmaps that show the most important words that impact the classification of the convolutional network. For this paper, we have explored how can the visualization module be extended to accommodate different kinds of explanation generation methods. In addition to GradCam, which came out of the box in the CNN implementation that we have sourced, we have coded a sharp and line explanation generation module. In the remainder of this presentation, we will focus on those additions and how they were assessed by the evaluation group that consisted of professional lawyers. As for the dataset used, as already mentioned, we have settled down on using the well-known PTSD dataset. It is a collection of 50 judgments coming from the US Board of Veteran Appeals. Each sentence of those judgments was annotated by human annotators according to the rhetorical role that those sentences play in the judgments. There were 6 roles distinguished, and the exemplary sentences are shown at the bottom of the slide. Our convolutional network was trained on this set, and we achieved relatively good accuracy of about 83%. Though we really did not focus on the efficiency of the classification task, as our main aim was user-based evaluation. Nevertheless, we conclude that those results in terms of accuracy are already satisfactory, and we believe that they can be improved down the line when more work is put in this area. The most important part for this presentation was the fact that the network was used to generate explanations in the form of heat maps, as presented here on the slide. Each explanation method generated a distinctive set of heat maps. We have chosen 6 sentences from the PTSD test set that were correctly classified by the network, and explanations were generated for each of those sentence types. Like 3 explanations were generated, each for GradCam, Sharp, and Lime. To assess the usefulness of those explanations, we have prepared a survey which was circulated among legal professionals. They were instructed that the computer mark the parts of the sentences which were the most decisive for making a decision regarding the classification. The lawyers were then subsequently asked to grade each of the explanations on a scale 0 to 10, with 0 being worst and 10 being the best. The slide that is presented now presents an overview of the results for a sample sentence. Next to the sentence's heat map, we present the average user score, as well as the resulting, and we have also assessed the explanations in terms of the metric that comes from a computer vision. In the paper, we give a set of 2 metrics. Here, for this slide, we show the metric which in full is called fraction of elements of relative threshold, and this metric represents what portion of input data was taken into account by the CNN. It can be clearly seen that Sharp highlighted the whole sentence, while GradCam was the most selective method. So there were differences in our respondents' assessment of various methods. Statistical analysis shows that those differences were not statistically important. Therefore, it can be said that all the methods were assessed by our respondents similarly. And when deciding what method to use in a computer system, other factors should be taken into account. For example, from a software engineering point of view, it should be noted that implementation of certain method is dependent not only on user's voice, but also on technical feasibility. GradCam is a method that, to the best of our knowledge, works only with convolutional networks. Lime is a method that is dependent on a number of hyperparameter values, and there are papers that suggest that it can be tweaked to the point of showing anything that the programmer wants. As well as the technical merit is concerned, we have used open source libraries for implementation of different methods and have found that the quality of implementation is varying. Thus, this may also be a factor that can be taken into account. And finally, let me make some additional remarks. Let's return to the example that was shown on the previous slide. Here, it can be spotted the results between different explainable artificial intelligence methods vary widely. For example, when I have seen the results coming from Sharp, my first comment was that it has gone ballistic. Yet, there was a disagreement between the respondents, and 8 of them said that the results for the citation sentence given by the Sharp were the best, while 9 experts have graded it as the worst. Thus, there seemed to be an implicit disagreement between different respondents as what exactly is the best explanation. This can be further strengthened by different comments that we have received from the respondents after performing the survey. For example, one of the respondents has said that he did not do this part of the survey at all because he was confused by what those colorful words were supposed to mean. On the other hand, the other expert has said that it made him question how he thinks as a lawyer, because this classification task is something that he would do intuitively. He had implicit mental model of the task, and our survey made he question how that implicit mental model really works. In addition to the part that I have already shown, the lawyers were also asked a number of generic questions regarding their stance towards the artificial intelligence in general, as well as its usefulness in their professional life. This part was meant to elicit the requirements for such systems as provided by the respective users. The prospective users, the legal experts, were asked generic questions regarding artificial intelligence and explainable artificial intelligence, and we have also allowed them to freely write what they expect from AI-based systems in terms of justification. As far as the results go, we have in general found the lawyers to be enthusiastic towards the use of artificial intelligence in law. The tech cloud, which was already presented in one of the previous slides, showed the phrases that occurred in the answer most often. Artificial intelligence and law curriculum seems to have penetrated the ranks of the lawyers, as 90% of the respondents see them as useful. Remaining 10% had no opinion, and they were not negative towards the AI-based system. 62% of the respondents have acknowledged that they were already acquainted with the term explainable artificial intelligence. And 52% of the respondents believe that one has to understand the inner workings of the explainable system to receive meaningful explanation, which suggests that understandable explanation that do not that allow one to understand the system's decision without knowing its inner workings is something that needs to be worked on. This concludes my presentation. We consider that the work presented here can be a basis for deeper studies. We had 21 respondents, and obviously future work should include a larger user base. Explanations can be tested using different datasets and other visualization methods, and a more in-depth studies of lawyers' conceptualization of explanation should also be conducted. Most importantly, we think that means of introducing domain knowledge to the explanation should also be explored. Thank you for your attention.
Thank you, Lucas. And now we have a few questions from the audience. The first one, course stacking. The author of asks this. The authors of SHAP show in their NIPS paper that LIME is basically a subset of SHAP without the guarantee of accuracy and consistency. The only advantage that I know of is that LIME is sometimes faster. So why use both SHAP and LIME in your explanation model?
Yes, I agree that LIME can be thought as a subset of SHAP in a way that both of them are based on generating local explainable models. In my opinion, for the full overview, both of those methods should nevertheless be compared. I mean, if there is a method that is commonly used, and to my knowledge, LIME is such a method that I think that omitting it would be an omission in this paper. I don't know, would Sashi like to comment on this question as well?
No, I think you pointed it right, Lucas. So because LIME is also one of the commonly used methods, right? So we did not want to leave out of the comparison chat that we had, and we did understand that LIME and there's not greater difference between LIME and SHAP. They both originate from a similar principle.
Okay, so we can move on to second question from Trevor Bench Kaplan. All words highlighted got a score of nearly 5 to 10. This suggests that the users were rather undermating. Would no words highlighted also get 5 to 10? And after, I think the third question will be easy. And from Sabine Weinhardt, how large was the pilot?
I think I should have mentioned that in the conclusion, it was 21 respondents. Yes. And as far as the second question go, the scores of about 5 out of 10 that I have shown on the slides were the averages that we have received. And we have found that the users, when concrete answers by concrete users were explored, they were much more divided regarding their assessment. So the people tended to give high score to certain methods in certain explanations and low scores to other ones. So that 5 out of 10 is just an effect of averaging that was presented here in the results. Thus, based on the individual answers, I can speculate that no what's highlighted would be graded as zeros by the respondents. But this kind of control sample might be good to be added in future studies to see whether they really give it a score of 0.
So I have another question here. Is it possible to notice that lawyers who are not used to the concept of IAAIL and participate in the survey got more enthusiastic or somehow disappointed with AI in your point of view? Which were their expectations when hear about AI?
The answers that we got, I can make the conclusion based on the answers that we got, and the answers we got were generally that they were enthusiastic towards the artificial intelligence, and 90% of them has shown that that they see the use of such systems. And many of the lawyers have also said that they were knowledgeable of the term explainable artificial intelligence. And I must personally say that I was a little surprised with the results. In general, as I have already said, they were enthusiastic towards the artificial intelligence and have seen this as a method that will take away the burden of manual work from them. But I think that this is something that every professional group may expect from artificial intelligence.
Okay, and I have another question from Trevor. How can every word highlighted explain anything?
I completely agree with that comment. As I have said, when I have seen the explanation given by Sharp, my conclusion was that it is useless. Nevertheless, many of the lawyers have highlighted this as the most important. I think that this shows how the concept of transparency and explanation differs between different particular lawyers. So a more detailed inquiry should be made. To test what lawyers really want from such an explanation. My hypothesis was that in case of the explanation that marked all the words, the 8 lawyers that said that it was the best explanation wanted the most complete set of words from a given sentence. Like for the citation amounted not only to the reference to a judgment that was cited there, but also the summary of the points that were coming from the judgments. and maybe for those lawyers, only that offered a complete explanation of what the system did. At least that's my hypothesis, and as I have already said, this deserves further inquiry.
And another question from Malte Ostendorf. Did you see any difference how useful the explanations were given, a correct wrong prediction from the model?
The short answer is no, and the longer answer would be that we did not test that. When we presented the explanations to the lawyers, we took only the ones that were correct, because we thought that the incorrect ones may be somehow confusing to the lawyers, and this is something that might be explored in the future work.
I have one last question. I have one last question here. Trevor, did you ask any of the respondents about what they like in the explanations?
That was not a part of our survey. The only part that allowed them to get a free input from them was the one regarding what they expect in general from explainable artificial intelligence system. I did talk with some of the respondents after they performed the survey, and as I have already said, one of the responses I got off the record was that it was an interesting exercise in analytic philosophy, because it made him really think deeply how he thinks as a lawyer.
So I think we don't have any more questions. That is no further question here. And I want to thank you, Lucas, for the great presentation and the answers. So unfortunately, now we have to move on to the next presentation. And I think Malte is already here. So now I'd like to introduce you Mr. Malte Ostendorf, who will present the second paper of this panel with the title Evaluating Document Representation for a Content-Based Legal Literature Recommendation. Mr. Malte Ostendorf will have 20 minutes of speech. Afterwards, we will move on to the questions. The floor is yours.
Yeah, thank you for the introduction. My name is Malte Ostendorf, and I'm presenting our paper, Evaluating Document Representations for Content-Based Legal Literature Recommendations. And this is a joint work with Elliot Ash, Terry Ruers, Bela Gibb, Julia Moreno-Schneider, and Georg Rehm. In this research, we explore how state-of-the-art document representation techniques perform in the context of a legal document recommender system. So why did we conduct this research? Literature recommender systems help legal professionals to find relevant literature, and they are getting more and more important as more and more literature is getting available. And in the recent year, there have been much progress in the technologies that underpin recommender systems, mostly based on deep learning approaches like transformer models or graph embeddings. So the question is whether these improvements are also beneficial in the context of a legal recommender system. Besides the technical aspect, we conduct this research also with reproducibility in mind. In general, recommender system research is known to have a reproducibility issue. And this issue also exists for legal recommender systems, where evaluations are often based on a small-scale user study, and also the evaluation data is rarely published. And this leads to inconsistent research results and makes it very difficult to actually reproduce the research. And that's why we set ourselves the following two research objectives. First, we want to evaluate a large variety of state-of-the-art methods. And second, we want to use publicly available data sets so we can make our work reproducible. This brings us to the data sets that we use in our experiments. We have three main criteria for the data set. That is an open license that allows us to share the data without any restrictions. And the data set should be also sufficiently large and also reflect different information needs. The large coverage of the data set is especially important when we want to compare fundamentally different methods like text-based against citation-based methods. We found two resources that fulfill these criteria, namely that is Open Casebooks and Wikisource. Open Casebooks is a platform from the Harvard Law School library where users can create and share open license casebooks. Their corpus consists of around 200 casebooks containing 3,000 cases. And the casebooks cover broad topics, but also rather specific ones. The cases from Open Casebooks are linked to the Case Law Access project. So based on this, we can retrieve full text and also the citation data for all the cases. After some cleaning procedure, we end up with relevance annotations for 1,601 court decisions for this data set. Our second data set is Wikisource. Here we utilize a collection of around 3,000 US Supreme Court decisions from Wikisource. Wikisource is a project like Wikipedia from the Wikimedia Foundations, and they collect original source documents. And this collection we are looking at is a collection of court decisions that is categorized in 67 topics, rather broad topics like antitrust or civil rights. A source for the full text and citations, we map the court decisions to the court listener corpus to have all the data available. And here, as a result, we have relevance annotation for 1,363 court decisions. But how do we derive relevance annotations from these data sets? In our experiments, we are considering a recommender scenario where we have a seed document and we want to know which other document would be a relevant recommendation for the seed. So as ground truth data, we need pairs of documents that are relevant for each other. And the two data sets provide exactly this information. For example, when decision A and B are in the same casebook or in the same wiki source category, we can say that A is relevant for B and vice versa. This relevance definition is, of course, limited. For example, one recommendation still might be relevant despite not being in the same casebook or category. That's why we rather refer to these data sets as silver standards instead of gold standards. However, the advantage is that this approach produces a large number of relevance annotation. For open casebooks, it's 140,000 document pairs, and for Wikisource, it's 200,000 document pairs. And this number is much larger compared to the user studies from related work. And it also enables us to evaluate a large number of methods. In total, we evaluate 41 methods and variations of them, and which 27 are actually presented in the paper. The remaining ones were excluded due to either poor performance or because they didn't provide any additional insights. The methods themselves, we distinguish them in 5 categories. First, we have a IDF baseline. Second, we have word vector-based methods like paragraph vectors or document vectors from averaged word vectors from fast text or GLAF. This is also known as mean pooling of word vectors. And here we test also different variations. One is kind of the original version of GLAF or fast text trained on a generic text corpus. And also one version where we train the word vectors on our legal corpus. We also test variations with an artificial total limit to make these methods comparable to the transformer methods. As transformer methods, we have BERT, REBERTer, different sentence transformer models. We have longformer and 2 separately published legal BERT versions. One from Chakaldas et al. From the Athens University of Economics and Business, AUEB, and one from Holzenberger et al. From the Johns Hopkins University, JHU. In addition to the citation text-based methods, we have text-based methods. Oh, sorry. In addition to the text-based methods, we have citation-based methods that utilize the citation graph to derive document embeddings. And lastly, we have hybrid methods that make use of both text and citation features. There is one approach that is the concatenation of document vectors from 2 methods. And also we have the score summation of similarity scores from 2 different methods. And as another hybrid method, we have a sentence transformer model that we train with citations as training signal. Before I dive into the actual results, some more words on our evaluation methodology. We separately evaluate open casebooks and Wikisource. And each of the tested methods here produces document vectors for all documents in the corpus. And then based on the vector representations, we then perform a k-nearest neighbor search to retrieve 5 most similar documents, which are then used as recommendations. For the evaluation, we then compare the C document and the recommendation candidate with our silver standards to determine whether it is a relevant recommendation or not. As a performance measure, here we have precision, recall, mean reciprocal rank, and our primary metric is mean average precision. Just as a side note, we set K to 5 because of the user interface where we want to deploy our recommender system. We also experiment with different K values, but found the results to be similar. All right, so let's start with the actual results. In this table, we have the tested systems, the dimension of their vector representations, and then the performance matrix for open casebooks and Wikisource. And we have the rank that's based on the average MIP over the 2 data sets. And this is also how the rows are ordered in this table. And also in this presentation, I will now only show parts of the actual table. So please look into our paper for the full version of it. On average, we have the hybrid score summation of fast text legal. So that's the fast text word vectors trained on our corpus, and the citation graph embeddings from point care, and they together have the highest MIP score. But if we view the data set separately, we have a slightly different outcome for open casebooks. It is the text-only method fast text legal that yields the highest MIP. Whereas for Wikisource, it's another hybrid method, the concatenation of fast-text legal and point care that yields the highest MAP. The other domain-specific word vectors like paragraph vectors or glove legal are also among the top methods. On the lower end of our table, we have the worst performing methods, which are sentence transformer models like Sentence Roberta or the citation method BoostNE. Now, for more insights, let's look at the method categories separately. Here in this table, we see all the word vector-based methods that we evaluated. At the top, again, we have the domain-specific word vectors that utilize the full article text. We see that also limiting the document text to a length that can be processed by the transformers does harm the performance, as we can see here with fast-text legal limited to either 4096 tokens or to 512 tokens. The other domain-specific methods like paragraph vectors or glove legal have shown a similar decline when limiting their document length, but are not listed here in the paper. But more important than the token limit is the in-domain pre-training of the underlying word vectors. As we can see here with the original glove and fast-text, those kind of generic word vectors were trained on Wikipedia or news text, so nothing was legal. As third category, we have our transformer models. And yeah, despite being very successful for many NLP tasks, one major weakness of transformers is that they are made to process relatively short text. So for example, in BERT, the limit is 512 tokens. In Longformer, it is 4096 tokens. And in our experiments, we have legal documents that are typically longer. So here we only can process the first n tokens of the documents that fit into the corresponding transformer model. And that's, of course, one limitation here of the transformer models. And to make the results comparable, at the top here, we have the legal, or fast-text legal version, where we have the similar limited token number. And exactly these two fast-text legal variations are also on average better than all other transformer models. Whereby for open casebooks, the token limit has a stronger effect on the performance. Here we have Longformer large, the best transformer model, and it also outperforms the 512 token version of fast-text legal. For the other data set, for Wikisource, the token limit is less critical. Instead, the in-domain pre-training has a greater effect. So here we have the two legal BERT versions are the best transformer models. And generally, we found that from the two legal BERT versions, the one from AOEB outperforms the one from JHU. And we see this reason for this outcome in a larger and more diverse pre-training corpus that was used from the one from AOEB. Similarly, we see that among all transformer models, the large version outperformed the base version. For example, here, Longformer or BERT. But yeah, overall, the performance of the transformers is relatively low. But one could expect that there might be a performance gain when, for example, you would train a Longformer model on a legal corpora. Yet these potential performance gains will most likely not justify the computational effort, in particular when we already have very simple and yet effective methods like averaging word vectors. And this is also what we found when we analyzed how the performance changes depending on the length of the seed documents. And there we found that even for short documents, fast text legal outperformed all the transformer models. In addition to the text-based approaches, we also evaluate citation graph embeddings. And in this category, we have a SPAT method, point care, closely followed by walklets. And overall here, we found that there's a strong dependency on the availability of citations. And that's why we say, or we suggest that these citation methods are actually better combined with text-based methods. And this is exactly also what our evaluation of the hybrid methods show. Here as hybrid methods, we focus on the combination of the previous best single methods, which are fast text legal and point care. Other combinations like glove and walklets have shown a similar performance, but they are excluded because they didn't provide any additional insights. The best methods in this category are also the best methods overall, and that is the score summation of fast text legal and point care. And again, here we also see a difference between the performance of open casebooks and Wikisource. While for open casebooks, the score summation is the best hybrid methods. For Wikisource, it is the concatenation of fast text legal and point care. Other combinations, especially the one from two text-based methods, like here fast text legal with long former, do not lead to the same performance gains as the combination of text and citation-based methods. And why the combination of text and citation improved the results is clear when we now have a look at the similarity of the recommendation sets. In this heat map, you can see the Jacquard similarity of the recommendations of two methods, where Jacquard similarity of 1 means that all recommendations are identical, and 0 means no overlapping recommendations. And what you can see here is a higher similarity between the text-based methods and also between the citation-based methods. But when you compare the similarity between text or word vector methods and citation methods, the similarity is low. So this means that they produce a different kind of recommendations. And this is also why combining them in a hybrid manner leads to this performance improvement. All right, so what conclusions can we draw from our experiments? First of all, document vectors from averaged word vectors achieved surprisingly the best results for all single methods. In particular, fast text word vectors trained on our legal corpus performed the best on both data sets. The training of such word vectors does also not require any special hardware like GPUs. And even when we introduced this artificial token limit, the performance of fast text legal was still comparable high. On the contrary, we have the performance from the transformer model that were rather disappointing. Of course, we have the weakness of the token limit, which is especially a problem when we have lengthy documents like these court decisions. And of course, there are promising research efforts like the long former that are capable of processing more tokens. However, right now, training such a model and especially applying it in a production environment requires much more compute resources. And these potential performance gains do not really justify these efforts. Much less effort actually does it take to combine text and citation methods in a hybrid manner. In our experiments, we use very simple approaches like the concatenation of vectors or just adding up similarity scores, and still outperformed all other single methods. Lastly, we also validated our quantitative findings based on the two silver standards with a domain expert who agreed in 70% with our silver standards. And this high agreement and also the large quantity of the two data sets makes them very interesting for future work, where we plan to use them to benchmark also new different document representation methods. All right. Yeah, thank you very much. Please feel welcome to look at our code and dataset. It's all available on GitHub. Yeah, thank you very much.
Thank you, Malte. And now I have some comments and questions here. I'm going to read for you, okay?
Sure.
First, from Sabine Wenhart. I just have a comment that I don't agree with your formulation of recommending legal literature. You did legal document recommendation. Legal literature shall refer to educational textbooks in law. Reading your presentation's title, I expect a different word, but still, I think what you did is impressive. Okay, you want to say something about that?
Yeah, of course. I mean, the term literature covers a lot, right? And in our example, we mostly focus on, or only focus on criticisms. So of course, this is kind of a subset of all literature, and I agree. Yeah, would be interesting to expand this to other, yeah, educational textbooks. This might be also something for future work.
Okay. And here we have a comment and a question from Trevor Benchcapel. These results all look pretty poor with less than 0.6 for precision and very low recall. Are these techniques useful at all? Even the best is not good.
Yeah, that's actually the generally low scores due to the silver standards that we used. I mentioned that this is also the reason why we refer to them as silver standards, not as gold standard, but because we expected that many actually relevant recommendations will be missed by our ground truth, by the silver standards. And this is also what we found in the kind of expert study, where we had one domain expert judging the recommendations. And there we also found that, yeah, relevant recommendations were missed, right? Where the domain expert said, okay, this would be relevant for me, but it was not part of the silver standard. And this is how kind of I would explain the low results. And kind of this is of course one weakness from the silver standard, but I see kind of the big advantage opposed to maybe a user study that is typically conducted, is that we have a much bigger quantity of actually recommendation pairs that we can compare. And this is also what we did in the paper. It's not really now presented in the slides, but kind of we also checked how the actual performance is changing when depending on document characteristics like the document length or citation count, which I would say to do something like this, you need, I don't know, a bigger evaluation corpus, which usually like a user study wouldn't provide. And, so this is kind of the, yeah, on one hand, like one weakness of our silver standard, but also one strength, right? That we, it's difficult, yeah, you have the low results, but on the other hand, you can perform more analysis on the data because you have more quantity.
Right. And we have a question here from Winkles. Perhaps users might find recommendation useful nevertheless.
Yeah, so maybe just as an outlook, so kind of what we did here was really just evaluating a lot of existing methods to have already kind of a limited subset of methods that we now in the next step want to evaluate in an actual live system, right? you probably can't really run like A/B testing on those 40 methods or something that we tested. So at first, we want to select a subset and then now compare the most promising methods in a more detailed study with real users.
I have a comment from Adam Weiner. I agree with Red Bull. It's very useful and important to have studies like these that reproduce, evaluate, and compare results. Okay. You want to say something?
Yeah, thanks. I agree. So that's kind of
okay.
the motivation behind it. That yeah, we found many existing work use user studies, but it's kind of difficult to reproduce, and that's why we thought to have these kind of openly available data sets, and now we can kind of continue working with these data sets and also then go and actually improve the methods for these data sets.
All right, and I have a question from Dennis Miller. Did you investigate how the results change with large K? Given the relatively close results, do they exhibit similar performance for more recommendations?
Actually, with larger K, the scores increase slightly. But of course, as you get to very large K, where they stop to kind of decline again. But yeah, as I mentioned, kind of this setting K to 5 was mainly chosen because kind of the service where we want to deploy this recommender system has kind of this restriction of just showing the top 5 recommendations in the user interface, and this was kind of the reason why we then in the end decided to just stick to this one K value.
Okay. So we have.
But yeah, sorry, kind of the second question was right if the actually relative results changed, but no. So kind of the ranking among the methods, especially among the top methods, it didn't change.
Okay. And so we have just 3 minutes left. If you want to make some final remarks, make yourself comfortable.
Yeah, maybe yes. Actually, if there is somebody who also runs like a recommender system in a production environment and wants to actually test kind of all the methods, and I don't know, A/B test or something. Of course, we are always looking for kind of partners who have access to such a system to run these experiments with real users. So yeah, I'm happy if there's somebody and yeah, who would be interested in doing such an experiment together with us.
So Maud, thank you very much for the talk. And so from now on, you have to move on to the next presentation with Dennis Almiller. And I'd like to introduce him to all of you. He is going to present the 3rd paper of this panel with the title Structural Text Segmentation of Legal Documents. Mr. Dennis Almiller, you have 20 minutes of speech. Afterwards, we move on to the questions. The stage is yours.
All right, thank you so much. I hope everyone can see the screen. And with that, I'm going to start with our full paper presentation titled Structural Text Segmentation for Legal Documents. So this is an equal contribution work between myself and my colleague Satya Almasian. And we have further collaborators Sebastian Lackner and Michael Gertz, also from the Database Systems Research Group in Heidelberg University. So to start with a brief motivation, what is structural text segmentation and especially given legal documents all about? So what we usually deal with in especially legal domain, we have plenty of unstructured document formats, for example, PDF documents. On the right, you can see one example of an end user's license agreement. And so if we look at this document, we can already see that it provides us with a natural segmentation of the context, right? So we have these paragraphs and then even like the headings with a different numbering provide some overview of how we as a reader should interpret this document. However, this kind of structure usually gets lost when we're dealing with a machine readable format. And even when we try to apply segmentation methods afterwards, usually such a paragraph or a document structure is lost. And why is this important? Well, especially for the segmentations, we have a lot of tasks nowadays, for example, in the workshop at this conference, where you're dealing with paragraph retrieval. So having like structured and thematically similar paragraphs is essential. You also have use cases for mergers and acquisitions, or last but not least, document search in general for just cases at like courts, meaning that once we can make sure that a segmentation of a document is still improved in a machine readable format, we're going to have a much better downstream performance, hopefully. And to illustrate this even more is, even if we have some completely nonsensical text, like a lorem ipsum example here, we're still going to interpret this as a semantically coherent unit, which is very important for our actual work here, because what we're now doing, and specifically comparing to previous work, is instead of focusing on a segmentation that bases itself just on a sentence level, this has some major problems. Specifically, there is a very narrow context given just by using a single sentence as a boundary. And the other question is, if we already have these thematical units like a paragraph, is it even useful if we split at a lower level, meaning the sentence level, than the paragraph level? And when we look first into this, specifically for the legal domain, there is a lot of hurdles that come with using existing methods. If you're looking at learning-based approaches, they usually come with custom architectures, which have like restrictive transfer learning capabilities. Most of them are some kind of hierarchical LSTM model, which is very difficult and unstable to train. You have exploding and vanishing gradients. And last but not least, they usually require large amounts of training data, which is not available in domain-specific applications such as the legal domain. And I think actually one of the major limitations that we encountered was not just using tools, but finding some of them. So they are really hard to come by. They either have no documentation at all, they are outdated. We had like one of the repositories that we tried to use that had only 20-year-old C code, no updated version was existing out there. And that was the most common scenario actually, we weren't able to find any code at all. So even if I wanted to apply this to a legal document, I would not have any working solution at the moment. And so this is where our work comes in with its core ideas. And so we have these three main areas that we're going to focus on. So the first one is relatively trivial in understanding what is happening here. We're simply moving the attention span of our segmentation model from a sentence level to a paragraph level. This gives us a much more natural transfer of what elements are existing in the text already. And they kind of serve as a natural boundary that we assume in our work. Similarly, this also introduces a much broader context window, which can be helpful for methods that rely on this contextual embedding. And last but not least, paragraph structures are also something that we can semi-automatically extract from documents that have some vague annotations, such as XML or HTML. The second step is actually more on the model for the segmentation itself, where we rephrase it from a purely sequential document segmentation, where you have one input sample of an entire document, to a pair of binary classifications, meaning we simply look at two subsequent paragraphs and predict whether those are actually thematically coherent. This makes it much more easy to train. This is more stable and has less problems of an architectural sharing. And it is comparatively cheap in that we can use pre-trained checkpoints to actually use existing models and retrain them to our purposes. Given that we now have a different model formulation, we also rely on a different sample generation. And we actually present two different strategies in this work that make it very efficient to sample from a small number of documents even, and that can generate many more samples than the number of documents that are available. We're going to talk about this in more detail, but first I want to just again reiterate from a theoretical point of view what exactly we mean by structural text segmentation. And so what we assume here as an input is usually some kind of document that has a natural structure in terms of the paragraphs here. And indicated here with the colors, we have first three paragraphs that are topically coherent, and then a fourth paragraph that is covering an entirely different topic. And now basically the task of structural text segmentation is to generate this labeling in the terms of colors that we do not have a priori. Again, what I already mentioned is that traditionally you would feed the entire document as one single sample and generate one single prediction for this entire document. This is already where we have the mentioned problems of long-range dependencies. So the question becomes, is it even relevant for the fourth paragraph? What happened in the first paragraph? And to exemplify this, in reality, you will have documents that are spanning several pages. And here, really, the context loses its meaning beyond just the immediate neighbors. Another downside, again, mentioned was the hierarchical training setup. To deal with the embeddings of single paragraphs and then predict over those paragraph embeddings again, you require usually very convoluted architectures that were used in related work that we try to abstract away here. So this is our rephrasing of the segmentation as a binary prediction problem called same topic prediction. And essentially, we make some form of Markovian assumption. So instead of relying on the entire context for the document, we just say, okay, we are training a classifier to predict whether two adjacent paragraphs are belonging to the same topic. Given our same sample document shown on the previous slide, what now happens is instead of a single forward pass, we're going to do at inference time 3 different predictions where we ask whether the first 2 paragraphs would be of the same topic, where the second and third paragraph are the same, and consequently the third and fourth paragraph are of different topics. So this immediately removes the overhead of the sequential nature that I've previously mentioned. And the other point is, if we look at how those samples are basically laid out, just having the neighboring samples, it becomes relatively trivial to just sample many more pairs of paragraphs from the same document. Again, just to highlight, we can still apply this to the entire document sequentially when we're doing inference later on. Okay, so now to the actual methods used in this work. I'm sure you've heard plenty about transformers this week already. I just wanted to mention why we use this specific architecture here. And there's a few points that we thought made sense from our standpoint. Firstly, those come as large and pre-trained architectures, meaning that we do not have to worry about long and expensive training ahead of time. And especially since we can continue from those pre-trained checkpoints, it is much easier to achieve state-of-the-art results. For the fine-tuning as a binary classification task, the architecture basically looks like this, that we feed in 2 separate paragraphs as a single sample, separated by a special token, and will retrieve a class label that is then the prediction of whether those belong to the same paragraph or not. A small implementation detail here, we're actually using Roberta because they have slightly improved performance on all tasks, but we have experimented with BERT as well in this work. Our second methodology is the so-called sentence transformers, which was introduced by Ramis and Gurevich. Specifically, this is a variant of the transformers, which uses this bi-encoder layout. And if you again look to the figure, what happens instead is that we're feeding only one paragraph in a forward pass, and then retrieve these embeddings U and B, and basically predict based on the comparison of those 2 embedding vectors U and V. The main advantage is that sentence BERT performs extremely well on embeddings and similarity tasks, which is shown in the original paper. And the more important aspect for our work here is that it also effectively doubles the input length. Because remember that for the BERT model, we can only feed 2 paragraphs in one pass. Getting back to the actual sampling of our training instances, we have 2 main strategies here. The first one is called random paragraph. And what we always do is essentially we sample from a reference pair, here denoted in purple, both a positive and negative sample. In the instance of random paragraph sampling, what we do for the positive sample is, or for both actually, we just aggregate all of the red paragraphs into one class and sample a random positive pair from this same topic, meaning that this can also come from another completely different document that has the same topic in it. The negative pair, similarly, will sample from all of the paragraphs across all documents, but from a different topic. And that the problem of this method is that it requires some cross-document normalization, where we basically have to actually normalize here and verify that these sections are actually the same across different documents. The improved strategy that we use is the so-called consecutive paragraph sampling. The name is slightly misleading, but essentially what we do is we restrict ourselves by just sampling from the same document 1 in this instance, where both positive and negative pairs have to come from within the same document, but however, still from either the same section or a different section. The main advantage is, again, that we now no longer require any cross-document normalization, which makes the annotation process for our initial training setup much, much easier. However, there is this one remaining question that we also want to answer in the experiments, that is whether it generalizes well to unseen topics, because now we do not have any relevance between the documents, which might lead to a much poorer generalization. Talking about the data set that we used in this experiment, we actually obtained a new terms of service data set from website terms of services. So the main point being that terms of services always have to be available from the landing pages directly, making them relatively easy to extract. And the other benefit is that while they focus on a legal context, they have relatively similar structures and topics across many different documents. So we will obtain, for example, shown on the right, around 20,000 of the documents that have a limitation of liability clause in there. And similarly, we normalized all the other sections as well. This is only an excerpt of the most frequently appearing one. But there is many more because we extracted overall around 40,000 documents based on this Alexa top 1 million list of English websites, from which we then automatically extracted the hierarchical information that was available in their terms of services, which includes linking different paragraphs to a specific section. The one manual annotation that we had to do for our random paragraph sampling is the mentioned cross-document normalization. Specifically, limitation of liability usually was spelled in 3 or 4 different ways. You had limitations of liability or liability just as a single word, referring to similar topics that were manually grouped together. And after all the pre-processing, we're left with around 40,000 usable documents, depending on which task specifically we're looking at. The average length being around 22 to 23 paragraphs and around 3 sections. Now actually moving on to the experiments. So the evaluation that we did was firstly verifying that our binary classification actually works well, and then transferring this into an actual downstream segmentation task. The setup that you're seeing here are the basic methods that we compare for both the classification and segmentation. We will introduce further related work in the actual segmentation task. But for now, baselines that we used are simply averaging glove embeddings. In the previous presentation by Malte, we've seen that this usually leads to really good performance out of the box. Similarly, bag of words and TF-IDF vectors are a good approximation and turn out to be actually competitive with related work. But what we specifically are interested in is fine-tuning transformer models, where we choose a Roberta-based model with a classification head, so the so-called ROCLS model, and then a sentence transformer variant of the same Roberta-based model called STRO. As a brief side note to the hyperparameters, we usually sample 3 positive and negative pairs from this per paragraph in the document. And we run all models from 5 different random seeds to account for any statistical variance in the training procedures. Training is performed over 2 epochs for the transform models, and generally our 80-10-10 split is consistent for training, development, and testing. Now, looking actually at the same topic prediction task performance, we compare both the different models and the different sampling strategies. One slight caveat to this is because we sample differently both for the validation and test sets, we cannot compare models between random paragraph and consecutive paragraph sampling here. However, we will still be able to compare those on the next slide when it comes to downstream performance. What we will look instead is how these models perform across like the board, meaning basically we can still look at how glove averaging performs in comparison to the, for example, sentence transformer models. And we see that the sentence transformer models for both strategies perform extremely well, much better than any baseline, and specifically show a better performance, although only slightly better for consecutive paragraph sampling compared to the standard transformer models. Generally, what I want to highlight is also that random paragraph sampling seems to have some inconsistencies in the training stability, which can be due to a variety of reasons. However, we noted a large variance in the performance that was actually subpar to some of the baseline methods. Going on to the actual segmentation and then circling back to the tasks that we actually wanted to solve here. We have this traditional segmentation metric called the boundary error rate PK, which is frequently used in other segmentation works. It gives essentially a probability of 2 samples being incorrectly labeled when compared across the document. And this means the lower the error rate, the better the method is. Furthermore, we introduced two related works for which we could find working solutions. One of them is GraphSec, an unsupervised method introduced by Glavash et al. That is usually also working on sentences. And similarly, Wikisec, Koszorek et al.'s supervised segmentation model that was trained originally on Wikipedia data, for which we do a training from scratch to have no advantageous embeddings. What we can still see here, and which is consistent with our expectations, is that the consecutive paragraph sampling for every method performs significantly better than the random paragraph sampling. So specifically for the transformer-based method with this classification head, we see that the consecutive paragraph sampling is indeed more stable on the downstream performance as well, and almost competitive with the sentence transformer model from the both from the random paragraph sampling and consecutive paragraph sampling. Similarly, all of the transformer models, with the exception of the unstable Roberta CLS model, outperform the baselines as well as the related work. We do denote that while it seems that those results are extremely bad, this might be mainly due to the fact that they were originally designed to work with sentence inputs and not paragraphs, which is especially detrimental for the unsupervised method GraphSec. However, for Wikisec, we assume that there was also some implementation detail that we might have gotten wrong, leading us to the conclusion that those models would not have been usable by somebody trying to get segmentation on legal documents. Because we personally found this method to be rather hard to understand, what we also did is come up with an alternative evaluation metric for the segmentation, specifically on paragraphs, which is the so-called accuracy up to K. It's rather simple to explain. Essentially, we account for the fraction of documents that have less than or K mistakes. So this actually gives some relevance to our error rate seen on the previous page, because even though we tend to have rather low PK values, if we tend to look at the transformer models, which is this upper curve, even those have only around a quarter of the documents that were classified entirely correctly. Keep in mind, again, those are around 23 predictions that we have to do per document. However, if we account for only 2 mistakes, we can see that already 2/3 of the documents are classified correctly, which might make this still an acceptable segmentation for many downstream applications. But more importantly, it allows us also to give a generally more interpretable result, because even here we can see that the best performing baseline method, the average glove with consecutive paragraph training, is still significantly worse than the transformer models that we see here, with the one exception again being the very unstable Roberta CLS random paragraph sampling model that performs even worse than that. Just as a reference, before anyone would ask the question, we also just tried predicting what would happen if we just said, okay, all paragraphs belong to the same topic, which is the last red curve here, which is predicting simply just always the same topic. Yeah, and with that, we're coming to a conclusion of this presentation. So in summary, the main points that we introduced in this work is a simple but effective training strategy for document segmentation, specifically on paragraphs. We supply a new resource available to the community of web terms of service documents, and have shown in experiments that our proposed transformer binary classification models also translate extremely well to downstream performance tasks. As a brief outlook, what we can do in future work is essentially investigating the actual retrieval performance, specifically in long legal documents. So I've already mentioned in the introduction some of the use cases that might be applicable here. We're also working right now on a more general text segmentation model, which is trained on Wikipedia data, just to see how that compares, maybe also in a zero-shot setting with domain-specific data. And largely, we've already heard about other transformer models that have a longer input context, which might be beneficial for our training on paragraphs. So this is one of the options that we can pursue here as well. With that, here is a link to both our code and data, and as promised, you can easily use this model through the Hugging Face library. Feel free to check it out and give us feedback on our work. And with that, I thank you for your attention, and I'm happy to answer any questions that you have.
Thank you, Dennis. And now we have a question from the audience, from Sabina Wennert. Very interesting talk. I heard you had the data in a HTML format. Do you consider using any superficial cues, font size, boldface from the HTML in the addition to the text paragraph information?
That's a really good question. So what we specifically looked at, why we specifically didn't look at it is mainly because we use some of this information in the extraction of the hierarchy. So to determine the order between different HTML documents, it's not as straightforward as it might sound. Some of them use the H1, H2, H3 tags, which is relatively easy to extract headings. However, bold facing was sometimes used as a replacement, or similarly the font size. So we use this in the extraction process, but we actually do not consider this for the segmentation here. The other reason for that is also because we want this to be applicable to not only websites, but also more specifically to any form of document that might not have a similar normalization. So I have worked a lot with PDF documents and can confidently say that even though you might have a larger font size, due to a different font, it might actually appear smaller. So this does not necessarily correlate to the actual interpretation from a human perspective here.
Okay, and you have another question. You make a reference to Wikipedia in the article, which studies terms of service. Both examples are sorts of texts that summarize information, organize them in a stiff recipe. Such texts follow consistently a pattern of structure very different from, for example, Superior Court judge rules. Are not those findings in structures limited to a more simple chaining of argument? Would it help too with understanding more complex structure?
I mentioned one of the main reasons why we use the terms of service documents is because we can confidently obtain a large number of documents, which is originally required to train our models here. I agree with you that those tend to follow a similar structure, and the problem is mainly that we do not have access to a large enough like supervised / annotated data set with complex cases. I would be very interested in this, and this kind of relates to the future work that we plan to do, where we evaluate an actual retrieval setting, or I'd say like downstream performance of our segmentation models. So yeah, I agree, but this is basically one of the limitations that our work currently has.
Let me see if I have further questions.
Maybe in the meantime, I can also add to this from a perspective of the related work that has done the training on the Wikipedia data, the Wikiseg model. In their own paper, they actually evaluate both within Wikipedia, but also have external training sets that are not necessarily more difficult, but certainly from a different domain. And even there, they tend to beat related work, or at least be on par in performance. So this gives us some hope that our model actually translates well to more complex cases as well.
Okay. All right. So we have a few minutes left. If you want to say a few more words, and Dennis, make yourself comfortable.
Yeah. So again, thanks for your attention. And I think the main issue that we're still looking for is a suitable downstream application where the segmentation can help directly. So if you do know of any shared tasks, or specifically have your own collection of documents that would benefit from such a segmentation, feel free to reach out. And with that, I think that's it from my side. So thanks again for the opportunity to present here.
Thank you, Dennis. And in name of ICAIL organization, I'd like to thank all the speakers of the first panel. And now we have a short break, and we'll be back at 11 o'clock GMT for the second panel. Those who want to meet other participants and exchange experience can access the Gather Town platform for a networking moment. The link is at the Open5 platform. Thank you very much, and have a nice day, everybody.